So what we're working on today for our day 5 notes is we are doing some more applications with your exponential functions. We're doing a few more than the ones we did last class. If you remember last class, I gave you 3 formulas you need to memorize for your quiz. Who remembers one of them? No. You're telling me A per. Yes, that's one of them.
Oh, P parentheses 1 plus or minus.
No. 1 plus.
Oh, they're 2 separate ones. Plus, I think N over C. Or R divided by N. Power of N T. Yeah.
All right. What was the first one that I taught you last class? A b to the x. There we go. So you got to memorize those, especially for Friday on your test. You're not going to be given them. You have to know those ones. So let's take a look at our notes. These problems are slightly different than the ones that we dealt with last time. They are going to still kind of follow the a times b to the x ruling. It's just it's going to have some extra parts to it. So we have a liquid that starts at 200 degrees Fahrenheit and begins to cool in a room that is at a temperature of 7 degrees Fahrenheit. So let's think about that for a second. What's going to happen? Let's say it's my coffee. I put it in a room that's 70 degrees and I don't drink it. What's going to happen to my coffee? It's going to get cooler. Where is it going to stop cooling to? Room temperature, which in this case is 70 degrees. This is kind of a little bit of science lesson. So your coffee is going to cool down to your 70 degrees. Will it ever go lower than 70? No. So it's going to cool down to whatever the room temperature is. Let's say the room temperature was 70. Or so let's say it was 20. It would cool down to 20, even though that's really cold for coffee. Especially right now. You got to drink hot coffee, no liquid or no iced coffee right now. So they want us to draw a rough sketch of what you believe the liquid's temperature function looks like as the time increases. So what does it start with? 200. So our y-intercept is going to be 200. It starts at 200 degrees Fahrenheit. It cools down, as we said, to 70. So I'll say on my scale, 70 is approximately there. So when it starts cooling down, will it be slow at first or will it be fast and then slow down? It starts cooling down and it'll be faster at first, and then it slows down and it levels off at about 70. So this actually ends up being an exponential decay formula. So based on the graph that we just drew, why would a times b to the x not model this situation? Danielle? Not quite. A times b to the t. If you graphed it, what does that get closer and closer to but doesn't touch? 0. Our graph, though, gets closer and closer to what? 70. So a times b to the t does not work because our graph doesn't go below 70. So that's why our normal equation doesn't work. So since our graph doesn't go below 70, we have to put a little plus c at the end of that equation. So it's the same equation. We're just going to have a plus c. And in this case, our c would be 70. Since we can't go below 70, that means we're going to do plus c plus 70. So that moves our entire graph up so that our graph now won't touch or cross the 70. It'll get very, very close, but it won't actually be 70. So for this graph, we know that at time 0, our coffee was 200 degrees. But that's not the a value in our equation. So if you think about it, our equation is a times b to the t plus 70, because we know our c is 70. Our time we said is what? We said our time was 0. So if I put a 0 in for the t of my equation, what happens to our b there? Turns into a 1. When I multiply it times the a, what do I have? So our 200 would go in for the function. So instead of f of t equals, it would be 200 equals a plus 70. So we would have to subtract our 70. That gives us our a value, which would be 130. So you don't have to go through that every single time. If you just remember at time 0, whatever that is, subtract your plus c, that's going to give you your a value. So now our equation is f of t equals 130 b to the t plus 70. So what's the last letter we have to find out? B. That's what we're going to find out in the next part. They gave us another time. They said f of 5 equals 153. So we're going to put 153 in for our function. So 153 equals. We're going to put 5 in for our t, so it's going to be 130 b to the 5th plus 70. So let's solve for our b now. So what do we want to do first? This goes back to these kinds of equations we were doing back on the second day. Subtract our 70 first. So I get 83 equals 130b to the 5th. Still got to get b on its own, so how do I get rid of 130? Divide. We're going to get a big, huge, long decimal. Write the whole decimal down when you get it. Thank you. So now I have b to the 5th. How do we get rid of the 5? Yes, it is. Yes. How do we get rid of that 5? We raise it to the 1/5 power. So go ahead and do that decimal to the 1/5 power. We want to round our answer to the nearest hundredth. So give me 2 numbers after that decimal. 0.91. So we now have our b value. So our function, if they had asked us to write it, would be 130 times 0.91 to the t plus 70, based on the information that they gave us. So let's take a look at our next one. We have a cup of hot tea is placed in a room. Temperature of the tea is measured every minute. A model for the tea temperature is given by this formula here. What is the temperature of the tea after 1 minute, 10 minutes, and then 60 minutes? So since they want us to find it out so many different times, what would be the fastest way to do it? But into what part of the calculator? Put it into the y equals. Let's look at the table. It'll give us the values for every single one of those points. It's going to make it a lot faster than to plug in 1 for t, then plug in 10 for the t, and then 60 for the t. So go ahead, type that into your y equals. All right, so under your y equals, we're typing in that equation. So once you have it in there, go to your table, and let's look for 1 minute. Let's round to the nearest hundredth. So to the nearest hundredth, what do we get for 1 minute? 73.92. So then scroll down, go to 10 minutes. 58.36. Now you could sit here and just hold your down arrow until you get to 60. Or you can do a little trick that's going to make it faster. Above window in blue is TBL set. That means your table set. So if we go to table set, you want to start at 0. The second line, let's have our table go up by 10. That's going to make it a lot faster for you. So now when I look at my table, I go 0, 10, 20, 30, 40, 50. There's my 60. It's a lot easier to get to your 60. So you would go to second window. I want to start at 0 and then go up by tens. So then for 60 minutes, that's another way you can do it. So now what is the temperature of the tea after 2 hours? But our table is in minutes, so how many minutes are we looking for? So again, if you've changed your table to be going up by tens, it's a lot easier to get to 120. So 20.60, yep. The one thing with the temperature is if you didn't use your table, if you were going to plug in every single number, and you got to remember still to plug in 120, not the 2. If you plug in 2, you're saying you're plugging in 2 minutes, but we wanted 2 hours. I said you can, but the table sometimes goes faster when they want multiple values. All right, so next question. What was the temperature of the tea when you first brought it in the room? So when time was 0. 76. So if a general exponential is given by y equals a times b to the x plus c, how can you easily find the starting initial value? So yes, you could sit there and you could plug 0 and figure it out. You could even go to the table, figure it out by looking at 0. But a faster way to do it, when we're looking for our starting initial value, that's when x is 0. So if I put a 0 exponent in, as we said before, what happens to our b? It turns into a 1. So our initial value is just your a plus your c. So if I went back up here to this first equation, my a was a 56, my c was a 20. 56 plus 20 gives us our same initial value of 76 that we would have gotten by plugging in 0 or by looking at our table and going to where x was 0. So that's just a faster way, just by looking at the equation, to be able to figure out your initial value. And then our last question on this page, what is the significance of the 20 in this question? Yes, but why? It's kind of like that first question. I'm placing it in a room. That's my room temperature this time. The 20 is your room temperature. They wanted you to put it in significance with the situation. Context, that's the word I was looking for. Context of the situation. So the 20 in this situation is room temperature, which is really cold. Really, really cold. I know. All right. So half-life, we're not going to talk too much about half-life, but we do have to talk about it a little bit. So when we're dealing with half-life, what you always have to remember is it still follows that a times b to the x power. It's your room temperature, Emily. It's your room temperature. So with our half-life problems, our b value is always going to be 1/2, whether it's 0.5 or the fraction 1/2, whichever way you want to use it, doesn't matter. But your b value is always going to be 0.5 when they're talking about half-lives. So as soon as you see that word half-life, first thing you should be thinking, my b value is 1/2. So in this problem, we have fluorine 20 has a half-life of 11 seconds. Write your own exponential equation to model this and find the amount of fluorine 20 left from 40 gram sample after 44 seconds. Be careful of your exponent. I have a lot of people when they read that, first thing they do is they plug in 44 as their x, but that's not going to be your x value. How many grams did we start with? 40. So our A value is 40. Since it's a half-life problem, our B is 0.5 always. Now what you have to figure out is how many times did it break down in those 44 seconds. So if I take my 44 seconds, divide it by the 11 seconds that it takes for a half-life to occur, how many times did it happen? So 4 half-lives occurred in those 44 seconds. That's what your exponent is. Your exponent is how many half-lives happened. So now you just do 40 times your 0.5 to the 4th power. And we get 2.5 grams. So that's how much would be left after the 44 seconds is 2.5 grams. All right. And then our last part of our notes today is a commonly asked question is, what kind of growth rate or decay rate do the problems possess? So you have to be able to look at your equations and tell, first of all, whether it's growth or decay, and then what is the rate of growth or decay. So sometimes it's really easy. If you have an exponent of just x, like our first 3 examples have, it's really easy to be able to tell. You just want to look at your b value. This b value is greater than 1, so this one's a growth. So to figure out what our growth rate is you subtract the 1, so we'd be left with 0.04, and then just move your decimal 2 places to the right, and you'd get your percent. So that one's a growth rate of 4%. How about 2 with a value less than 1? Would it be growth or decay? Good. So this one's a decay. Now, some people can look at that right away and they automatically know what the decay rate is. If you can, that's awesome. If not, what you need to do is take 1, subtract your decimal from it. So 1 minus 0.80 gives us what? 0.20. So now you move your decimal 2 places to the right. This is a decay of 20%. So how about a third example, growth or decay? Decay. So again, I'm going to do 1 minus my decimal to figure out what my rate of decay is. 0.05, which would be 5%. So that has a decay rate of 5%. So I said, those ones are a little easier. When your exponent, however, is not just an x, like our next 3 examples, you have a little bit more work to do. What we have to do is we kind of have to break apart that exponent so that we do have an exponent that is just x. So here I have a 2x. So what we're going to do is we're going to pull that 2 inside the parentheses and leave the x on the outside. So we're just separating our exponent there. So now using your calculator, figure out what is 1.04 squared. So now that I've fixed it and it's an exponent of just x, like our other 3 examples, now you can answer the question. So is this going to be a growth or decay? Growth. So I take the 1 away, move my decimal 2 places to the right, and it's 8.16%. Or I had some people around last class, 8.2%. That's fine also. Looking at our next example, we have an exponent of negative x. So you got to remember, that really means it's negative 1x. So how would we separate it? What would we want to bring inside? The negative 1. So 0.80 to the negative 1, leave the x on the outside. So go ahead, use your calculator. What's 0.80 to the negative 1? 1.25. So this is important why you don't actually answer the question until after you fix the exponent, because it went from looking like it was going to be a decay problem to actually being a growth. What's our percent here? 25%. Now our third example there, that one's a little trickier sometimes to figure out how to break apart that exponent. X over 4 is the same as saying 1/4 x. Just as a little side note, if I had x over 6, that's the same as saying 1/6 x. Whatever it's being divided by, it's 1 over that number. So we're going to want to pull the 1/4 inside the parentheses. Leave the x on the outside, so we have 0.95 to the 1/4. You can use your calculator to help you out with that. .95 to the 1/4. What do we get? 0.987. Growth or decay? Decay. So again, 1 minus the decimal would give us what? I would have 0.013 just because I stopped before you did. So as a percent, this is a decay of 1.3%. So those ones are a little bit trickier to figure out.